So we've come to probability, and I'm sure you've heard of this before, but let's get a quick introduction into it. So I'm pretty sure we're all familiar with coin flipping. Whether a coin lands on heads or tails, generally it's a 50-50 chance. So if it's a fair coin, that is. And that means that there's an equal likeliness we'll get a heads or equal likeliness that we'll get a tails. So probability is a measure of quantifying the likelihood that these events will occur. That's what this is. 50% or 0.5 is the probability of us getting a heads at every coin flip. So why is probability so important? In statistics, data science, and AI, obtaining the probabilities of events is essential to making a smart or successful decision in the business world. It is what we call a calculated risk based on our probability. So the questions we can solve or ask with probability is, what is the probability of my marketing campaign succeeding? What is the probability customer A will buy products X, Y, and Z? So in conclusion, accurately estimating the probability given some information is our ultimate goal. So the probability scope or the topics we're about to cover in probability will include how to estimate probabilities using theoretical and empirical methods, the rules of probability, which include the addition and product rule, permutations and combinations, and lastly, Bayes' theorem. So stay tuned, you're going to have a very good crash course on all the important aspects of probability. So now let's talk about estimating probability. So we can do some empirical or experimental estimates. So let's say we tossed a coin 100 times. We'd expect something like the following: 45 heads or 55 tails. This gives us a probability of getting heads written as P of heads, that's a probability notation, is equal to 45 over 100, because we did 100 tosses, which is 0.45 or 45%. So empirically, the probability of an event happening is this: the number of times an event occurred over the number of trials repeated. That's exactly what we did here. So why isn't the probability after 100 experiments 0.5? After all, isn't it a fair coin? Well, it could have been, but due to the random nature of coin tosses, it's very much possible that we could have some degree of variation. However, if we performed 1,000 coin tosses, our results may be something like this: 490 and 510, which is a lot closer to the 0.5 that we're expecting. So let's attempt this in Python. I have the code for this, so I'll demonstrate it to you shortly after. However, let's just look at the results here. So what this says here is that this is a probability that we get from just a few coin tosses in the beginning. As we can see, in the beginning, it starts off being very, very much not 0.5. It goes from 0.1, but as the number of coin tosses increases, you can see it gets closer and closer and closer to the actual 0.5 value, which is what it's supposed to be. So as we can see, the more trials we attempt, the closer it gets to 0.5. So probability can also be measured as a percent. Oftentimes you'll hear people saying the chances of something is 55 or 60%. Technically and mathematically though, we always measure probability between 0 and 1. It's never smaller than 0 or never larger than 1. Okay, so note mathematically, as I said, we always work with this range. And that's how we explicitly state it here. So all probabilities of all events must sum to 1. So let's consider a 6-sided fair die. The probability of getting 1 is 1 over 6. As such, the probability of each number is 1 over 6. That way, let's go back to that. This way, if each number is 1 over 6 and we have 6 numbers, we get 6 over 6, which is 1. That's why all events must sum to 1, probability of all events. So let's look at another question here. It's a simple probability question. We have a bag of 30 marbles, 12 green, 8 blue, 10 black. What are the chances of pulling a black marble out at random? Okay, so we know there are 30 marbles, 12 plus 8 plus 10, and that's how we get 30 here. And we know there are 10 black marbles, so the probability of a black marble being pulled out at random is 10 over 30, which is 0.3. So that's it. Let's go back to this. So that's it for first basic introduction to probability. Next, we're going to look at the addition rule. So now, before we move ahead with looking at the addition rule, let's look at how I created some of those charts with the coin tosses in probability. So let's look at this file here, 5.3 statistics for probabilities. Let's bring it up. So first thing we have here is a small little function that basically just does simulates a random coin flip. And every time we get heads, we add 1 to a heads variable, starts at 0. And every time we get tails, we add 1. And in the end, it returns heads over the number of flips in total. So flips is defined as an input variable. So we have 15, let's just do 10 and see how many heads we get. We got 7 heads because it's 7 over 10. So let's try 100.55, getting closer. So let's try 1000, 0.478. So that's pretty close. So now let's use this function here, or coin toss function, and append the results here. So let's append 1,000 results to our list. This takes a little while to run, but there we go. So now we bring this into pandas, clean it up. So this is a tail here. Let's look at the head, first 15. We can see how it evolves. So it starts off at 0, which means that we're probably getting tails instead of heads. Tails again. Then we got our first heads, and you can see the probability just drastically went to 6, but eventually it approaches 0.5. So let's plot it. So let's do 1,000 before we go to 10,000, because 10,000 takes a little while to run. And we can see this is a very nice graph. You can see as how it alternates depending on how many coin tosses we do. But as you can see, the more we do, the closer it gets to 0.5, which is what we expect. So now let's take a look at the addition rule in probability. So probability and certainty. So from our random experiments, we get a very good idea of the chance or likeliness of an event occurring. Okay. However, it's still a prediction based on random experimentation, and even if an event is 99% likely to occur, we can still expect with some certainty that 1% of the event, those likeliness, can occur in 100 trials. So in a coin toss event, we have 2 outcomes, heads or tails. In a dice roll, we have 6 possible outcomes for each event. So we're going to use something called the omega symbol, which is this ohm sign. If you're an electrical engineer or physics student, you would know. The omega symbol is used to signify the sample space, that is all possible outcomes, and this is known as the sample space. So the sample space for the dice and the coin would have been the outcomes here. Okay. Exactly. This is how we define it mathematically here for coin and for a dice. So let's take a look at something called the probability of multiple events. So multiple events here means that we have 2 coins being tossed simultaneously. Okay. Our possible outcomes, or the sample space, is now for coin 1, coin 2, heads heads, heads tails, tails tails, or tails heads. So we have 4 possible outcomes. As we just said, we have 4 possible outcomes with a 1 in 4 chance of each one happening. These are the probabilities of each right here. So now let's take a look at how the rules of probability are concerned with multiple events. The example, rolling 2 dice. So the first part we look at is called the addition rule. So let's roll a dice and answer the question, what is the probability of getting 1 or 6? Well, we know it's 1 over 6, 1/6. Basically, the probability of getting a 1 or a 6 is the same, okay? However, getting the probability of both, either 1 or 6, is the summation of both of these. So we add 1 over 6 and 1 over 6, we get 2 over 6, which is 1/3. So the probability of getting a 1 or a 6, which means we're getting a probability of either 2 numbers in a die, is intuitively 1 over 6 plus 1 over 6. So that's the addition rule. So here it is mathematically defined. Probability of A or B is equal to probability of A plus probability of B. This is also written as this, A union B. As this rule works for 2 or more events, this also holds up here. As you can see, mathematically we expand it to this. So here's another example. Again with our bag of marbles. So we have 30 marbles, 12 green, 8 blue, 10 black. what are the chances of pulling a green or blue marble out of the bag at random? So that's green, probability of green with blue or blue. So we have 12 over 30 plus 8 over 30, because we have 12 green and 8 blue. So that gives us 20 over 30, which is 2/3. So there's a 2 in 3 chance of us getting either a green or blue marble out. So here's a bit more about the addition rule. So previously, the events we looked at were mutually exclusive, and that means both outcomes cannot both happen at the same time. As in, we can't simultaneously pull a green and blue marble, like there's no half green, half blue marble out of that bag. So we can illustrate this by using a Venn diagram to show that there's no intersection between the events, like this here. A is separate to B. So here's another example of a mutually exclusive event. Let's say we have a class of 13 students, 7 female and 6 male. We're forming a small committee involving 3 of these students. What is the probability that the committee has 2 or more female students? So let's just go over this example quickly. So we have 13 students, we're pulling 3 at random, and we want to know what's the probability of 2 of these 3, at least 2 of these 3, being female students. So let's consider the events that allow this possibility to occur. Event A, which is 2 females, 1 male is chosen, and event B, which is 3 females are chosen. So these are the 2 events that allow us to get this probability, that satisfy this question here. So these 2 events cannot occur together, meaning they're mutually exclusive. They both can't occur together. Either one has to happen. So here's an example of a non-mutually exclusive event. So here's the illustration in the set diagram here. Now these events can occur together. So what's a good example to use? Let's look at cards. So now we have this question here. We have a deck of cards and we pull at random a card. What is the probability of that card being a king or hearts? So the king of hearts does exist. So they both can occur together. So he does exist somewhere here. So let's take a look at this. So the probability of a king, which will equate to being P of A, they have 4 kings in a deck of cards, so it's 4 over 52, 52 being the total number of cards in the deck. Probability of hearts being 13, because there's now 4 suits, so that's 4 divided by 52, which is 13. Remember, there's hearts, diamonds, clubs, and spades. And the probability of A and B occurring together, which is you getting the king of hearts, which is represented by this, and is this, and or is this, by the way. So it's 1 over 52. So technically now, the probability of A or B, which is what the question is asking, is equal to this, 4 over 52 plus 13 over 52 minus the intersection of P and A and B, which is 1 over 52, which gives us 16 over 52, which we can further reduce to 4 over 13, which is 0.31. So there's a 0.31% chance of us pulling a card that is either king or hearts from a deck of cards. So this is exactly the formula we discussed in the previous slide. The probability for non-mutually exclusive events, the probability of A or B occurring is the probability of A plus the probability of B minus the probability of A and B occurring. So let's look at some other probability problems. What is the probability of pulling 3 aces in a row? So now there are 4 aces in a deck of cards. So the probability of getting 1 ace is 4 over 52. So you would think the probability of getting a second ace would be the same. However, it is not. There are now 3 aces left and 51 cards. So the probability of getting 3 aces in a row is 4 over 52 multiplied by 3 over 51 multiplied by 2 over 50, which gives us this big number here, the denominator, and gives us this tiny probability of 0.0181%. This is an example of sampling without replacement. If we were to place the ace back in the card, this would be an example of sampling with replacement. However, each time we pull out the top card, like we get an ace, we don't put it back into the deck. So now let's talk about Bayes' theorem, which is a very important part of probability and statistics. So let's see this here. So at this point, if you're familiar or have taken statistics and probability class before, you'd realize we skipped over joint probability, marginal probability, and conditional probability. These are probability theorems that are used for two or more independent or dependent events. However, to teach this properly honestly requires a couple of hours of practice on your part. So what I'm going to do, I'm going to skim over this, kind of like give you the gist of each of them, and then introduce you into Bayes' theorem. So hopefully you can follow this class. If you don't, please let me know in the student forum below, and I'll try to address your questions. So let's look at joint probability first. This is a probability of two or more events happening simultaneously. Marginal probability is a probability of an event irrespective of the outcome of another variable. Example, the probability of a card being being a red queen. That's a probability of P, red and queen, which is 2 over 52. So this is how we represent it in probability here. So the probability of event X is equal to A for all outcomes of event Y. Now, conditional probability. This is a probability of one event occurring in the presence of a second event. Example, you pull the black card from a deck. What is the probability of it being a 10? So that's probability of 10 given that it's black. So that's now intuitively you can know that the probability of a 10 is 4 over 52, and there are two black 10s, so that's 1 over 13 in the end, 2 over 26. And that's how we mathematically describe it here. P of A given B, or P of A given B. This is the notation I think you'll see most common when referring to conditional probability. So now let's talk a bit about independence and exclusivity for these same conditional, joint, and marginal probabilities. Okay, so as you mentioned previously, it's possible for events A and B to be either dependent or independent of each other. If the events cannot occur simultaneously, this is called exclusivity. However, if they're independent events, they're not exclusive. So the joint probability of two independent events is given by this. And for events that are independent, the marginal probability is given by P of A is equal to P of A. And similarly, for conditional probability, if you want to get the probability of A given B, it's equal to P of A. These are all applicable for independent events. So now let's take a look at how independence and exclusivity are affected by exclusive events. So we know the joint probability, that is of two exclusive events, that is of both of them occurring together, is not possible, and therefore it's equal to 0. So the probability of A and B is equal to 0 here because they just can't occur together. It's impossible. The probabilities, it's like asking a deck of cards, what's the probability of a card being a 3 and a 5? Obviously it's not possible. So for probabilities of either event occurring, though, is given by sums. So P of A or P of B is given by this. This makes sense intuitively as well. If the events are not mutually exclusive, meaning that they can occur together though, probability of A given B is equal to probability of A. So now this brings us to Bayes' theorem. So I know we quickly went over joint probabilities and marginal and conditionals, so it all seems a bit vague right now, and I understand that. However, you can sort of get a gist of Bayes' theorem by just following in this next couple slides. So I'm going to read this theory for you. In probability theory and statistics, Bayes' theorem, alternatively Bayes' law or Bayes' rule, describes the probability of an event based on prior knowledge of conditions that might be related to an event. For example, if cancer is related to age, then using Bayes' theorem, a person's age can be used to more accurately assess the probability that they have cancer than it can be done without knowledge of the person's age. This is the definition on Wikipedia right now. And this is how we mathematically illustrate Bayes' theorem. So now here's an example of Bayes' theorem demonstrated. We're going to look at a simple cancer test example. So we know 1% of women have breast cancer and 99% of them do not. Now the test for breast cancer is mammogram, and 80% of mammograms detect cancer correctly and 20% of them are wrong. So now 9.6% of mammograms report cancer being detected when it is in fact not present. That's a false positive. So now let's look at a breakdown here. So for a positive test result here, there's an 80% chance that you have cancer, or the test is correct, and a 20% chance that it's wrong. And similarly, if you don't have cancer, the 9.6% chance the test is going to tell you have cancer, and there's a 90.4% chance the test is going to tell you don't have cancer. That's if you don't have cancer. So now let's suppose you or someone you know unfortunately tests positive for breast cancer. This means that it would have gotten the top row result here, positive test, all right? So now let's take a look at this. The probability of a true positive, which means that we have cancer and the test was positive, is 1% times 80%, which is 0.008, which is actually quite small, okay? Now the probability of a false positive, meaning that we don't have cancer and it was a positive result, which we know it was a positive result, is 99% times 9.6, which is 0.0954. So in reality, there's probably a much higher chance that the test was a false positive when you test positive for it. So remember, probability is equal to the event happening over all possible outcomes. So now we can intuitively say that the probability of having cancer given a positive test is 0.008 over the two outcomes we saw in the previous slide, okay? Because these are the top row outcomes we're looking at. And that gives us this, 7.8%. So the probability of you having cancer, given that you've got a positive result, is 7.8%. So now here's a breakdown of Bayes' theorem problem summary here, okay? Now I'm not going to go through this entirely. It's a slide you can pause and leave up, but this is how Bayes' theorem is written. So the probability of cancer being positive, given a positive result, having cancer, giving a positive result, is P of cancer given positive, and this is basically the formula for Bayes' theorem right here. And you can see what each one means right here and try it on your own time. Now there's a lot of tutorials and online resources that discuss Bayes' theorem in detail. This is just one simple example. If you want to get quite good at this, maybe pick up a textbook or some YouTube tutorials and go it over until you master it, because it's quite important theorem in probability and statistics.
Subscribe now and press the bell icon. Never miss an update.